space. It's far away. The commonly accepted boundary between our planet and space is known as the Kármán line, located around 100 kilometers above Earth's surface. But let's not just focus on official definitions. Let's consider the physical facts. Even at 10 kilometers above the ground, the atmosphere becomes just as perilous as space itself. Make even the slightest mistake, and it could cost you your life. Ever heard of a ghost plane? Take, for instance, Helios Airways Flight 522. While flying at 10 kilometers altitude, it lost communication with air traffic control. Fighter jets sent to investigate found motionless passengers and a steward desperately trying to regain control. Minutes later, the fuel ran out and the plane crashed. What happened? A tiny mispositioned lever caused all the air to silently escape the plane, leaving passengers with insufficient oxygen to breathe. It's a terrifying story, yet the allure of such heights attracts hundreds of people. Ascending to 10 kilometers, we leave behind what we commonly refer to as weather: rain, cyclones, storms, tornadoes, typical clouds, and most winds. Go even higher, up to 30 kilometers, and you'll find 99% of Earth's atmospheric mass below. See that thin blue strip on the horizon? We've grown accustomed to believing it gives us life, and all that mass above us certainly has a significant impact. Sure, it might seem like there's nothing interesting beyond, just emptiness, but that's not the case. The higher you go, the more surprises await. Your breath catches not only from the lack of air, but also from awe. You'll experience it with me, right from your couch or chair. The atmosphere of our Earth is divided into layers. The lower layers, like the troposphere, are conducive to life as we know it. Then there's the stratosphere. Beyond that, around 55 kilometers up, we enter the mesosphere, followed by the thermosphere and exosphere. The 100-kilometer Kármán line isn't actually the boundary of space. It marks a fundamental shift in flight dynamics. Below 100 kilometers, it's the realm of airplanes and hot air balloons, where lift from the air is possible. Above 100 kilometers, it's the domain of satellites and rockets. For NASA and the US Air Force, the boundary of space is around 80 kilometers, or precisely 50 miles. Legally, there's no universal definition of where Earth ends and space begins. Even satellites sometimes orbit at 80 or 90 kilometers, ignoring this line. At around 90 kilometers, the thermosphere begins, where sound disappears, because air molecules are so sparse that they must travel a kilometer before colliding with another molecule. Nobody would hear your scream up there. As we ascend higher, there's less and less air, but we can witness this thin air in the form of auroras. Beautiful. But what's happening here on a physics level? Tons of solar plasma slam into Earth's magnetic field, and a fraction of it penetrates the atmosphere near the poles. Furthermore, when atoms or molecules in the air are energized, they emit light of a specific wavelength, hence a specific color. By observing this color, we can determine the altitude of the aurora. Bright red, for instance, comes from collisions between solar wind and single-atom oxygen at the highest altitudes above 300 kilometers. Green, with hints of yellow, at altitudes from 100 to 300 kilometers, signifies diatomic oxygen, the stuff we breathe. And below, there might be a purple or pinkish band, indicating nitrogen above 100 kilometers. Auroras are actually quite hot phenomena, because we're talking about the thermosphere here. As you ascend into this layer, the air around you warms up with every kilometer. But what's causing this heating? After all, it's space. The thermosphere acts as a shield, protecting our planet not only from regular ultraviolet rays, but also from the nastiest, shortest ones, and even X-rays. They all slam into air particles, ramping up their speeds, which translates to temperature. That's the physics of it. Think of it like this. Soup is hot because its particles move around rapidly, transferring energy to your finger when you dip it in. But if soup maxes out at 212 degrees Fahrenheit, the thermosphere hits a scorching 4,500. Here's the paradox. When you get there, you won't feel the burn or the heat. Instead, you'll feel bone-chilling cold. Why? The answer's simple. There are so few particles hitting you that you won't feel their energy. Instead, you'll just feel the cold. It's easy to remember. In the thermosphere, there's a lot of energy in the particles, but there aren't many particles themselves. Not enough to heat you up, but still enough to buffet you if you're flying at high speeds. Take the Chinese with their Tiangong-1 space station. They lost control of it, and it plummeted from orbit in just 2 years. Why? Because even though the tiniest particles, 16 kilometers apart, were barely bumping into it, they collectively acted like concrete barriers on a road, slowing it down. In fact, the International Space Station, ISS, has to regularly boost itself with gas to stay in orbit. That's when astronauts experience a brief return to weightlessness, and objects start drifting ever so slightly. By the time you reach the ISS, you're flying 16 kilometers up and encountering just one particle. What else might you find up there? Well, the military found something. A giant mirror of sorts, for our radars. Short radio waves don't travel directly between continents from antenna to antenna. They bounce off ions and electrons, which are abundant in the thermosphere. Military radars, aircraft, and ships rely on this trick to communicate beyond the horizon. As we venture even higher, we enter the most intriguing realm. Beyond 600 kilometers, no lengthy expeditions are ever launched, because that's where the radiation belt begins. The only astronaut who can hang out there for a while is a dead one, as this is the prison for the meanest, most charged particles from the sun. Earth's magnetic field traps them and prevents them from frying our bodies, leaving them to float at this height. Besides these stray particles, hydrogen and helium from our atmosphere also roam this area, since the lightest gases rise upwards. So, that helium balloon you released at the graduation ceremony? It ended up there in the exosphere. Exo means outside, but let's call it the gateway sphere, because it's a real gateway between Earth and space, where even the faintest traces of our world vanish. A particle here can travel thousands of kilometers without encountering another. Many of them zoom so fast they reach escape velocity, 11 kilometers per second, breaking free from Earth's gravity. Imagine Earth as a pot of boiling water, with the hottest particles evaporating from the surface. Similarly, our atmosphere is constantly evaporating, losing 160 tons of gas every day. So where exactly does the exosphere end, and hence, our atmosphere? This is a fascinating question, answering which also solves a simple riddle. Who was the first person to leave the planet? Most would say Yuri Gagarin in 1961. But remember, he crossed the Kármán line, which is a conditional boundary. The atmosphere continues beyond that. Just a reminder, in the exosphere, individual hydrogen and helium particles float about. When sunlight reflects off these particles, it creates a glow. Observations show that this glow extends from Earth to a distance of 630,000 kilometers, technically including the Moon in Earth's atmosphere. So, the Apollo crews driving around on the lunar surface were still within Earth's boundaries. An astronaut could have taken off their helmet and breathed in the hydrogen and helium from their native Texas if it weren't for the lack of pressure. No one has ever truly left our planet in the language of physics. The first people who will truly leave our planet will be those who fly to Mars, and that's yet another reason to send an expedition there. Yes, we humans are so meticulous that we decided to count the atoms in the atmosphere, only to find out that our Earth is much bigger than we thought. It's astounding.